Hey everyone, today I'm presenting the paper Symbolic Execution with SymCC. Don't interpret compiled by Sebastian Pioplau and Aurélien Francillon from Eurocom published at USENIX Security 2020. This paper is about making a powerful security testing technique, symbolic execution, fast enough to go actually use in practice. By the end of this talk, I want you to understand what the problem was, what the solution was, and why it worked so well that it found two vulnerabilities that Google's own tools had missed. Let's get into it. How do you, yeah. So how do you find bugs in a program that you did not write? If I hand you a binary, a compiled program, and say, find the security vulnerabilities in this, what do? You can't just read it line by line, hoping to spot a mistake. Real software has millions of lines of code and billions of possible inputs. Manual testing is completely out of the question at scale. So the security research community developed two main automated approaches. And before I explain what this paper does, I want you to think about this question for a second. If you had to design an automated bug finder, what would your approach be? And how do you even start that? The two approaches that already exist are fuzzing and symbolic execution, and they sit at opposite ends of a spectrum. Fuzzing is fast, blind, and brute force. You throw millions of random or semi-random inputs at a program, watch for crashes, and just hope you get lucky. It's extremely fast. Tools like AFL can test over 1 million inputs per second. Symbolic execution is smart, thorough, but painfully slow. Instead of guessing randomly, it actually reasons about the program mathematically and solves for exactly what input would trigger a specific code path. The punchline of this paper is right there at the bottom. This paper closes the gap between them. So what is fuzzing? Let me make fuzzing concrete before we go further. A fuzzer has three jobs. First, it generates test cases. Lots of them, as fast as possible. Second, it runs the target program with each input. Third, it checks whether the program crashed. If it crashed, great. That's probably a bug. If not, move on and try the next input. The famous fuzzer AFL, American Fuzzy Lob, is so fast it can run hundreds of thousands of executions per second on simple programs. As you can see on figure 1 over here. This diagram from the paper shows the classic black box fuzzer loop. You have the target binary, a test case generator, execution, and output analysis watching for crashes. Notice what the fuzzer has no window into what's happening inside the program. It just sees crashed or didn't crash. That's what makes it black box. Fuzzing is incredibly effective at finding shallow bugs, things close to the surface, but has a big blind spot for deep, logic-specific bugs that only trigger under very precise conditions. That's where symbolic execution comes in. The key idea is, instead of running a program with concrete value, say input equals 42, you run with a symbolic value, call it x. You track what the program does with x, not as a number, but as a mathematical expression. Every time the program hits a branch and if statement, a comparison, you ask, what values of x go left and what values go right? You use an SMT solver, which is basically a very powerful constraint solver. Figure out the exact inputs that reach each path, as you can see in this diagram. So if your program say if x is greater than 100 to something dangerous, symbolic execution will automatically solve for x equals 100, 101 and generate that test case. A fuzzer might never stumble onto that value randomly. The landmark implementation of this is CLE. Published in 2008, KLEE automatically found bugs in GNU Core Utils standard Unix tools that had been manually tested for years in a matter of hours. To make the difference concrete, fuzzing is like wandering through a maze randomly, bumping into walls, occasionally stumbling into new rooms. It works, but it's inefficient. Symbolic execution is like having a map. It reasons about the structure of the maze and solves for the exact path to each room. This matters for a specific case class of bugs. Deep bugs, ones that only trigger under very specific conditions. Magic values, specific input lengths, checksums that have to match. These are exactly the bugs that the attackers care about. And fuzzing tends to miss them entirely. So why isn't everyone just using symbolic execution? There's one reason. I'll show you why. It is catastrophically slow, like way too slow. In the same amount of time that a fuzzer tests 1 million inputs, CLE or KEEE might test around 1,000. That is a 1,000 times performance gap. And this isn't like a minor engineering problem. It's not like CLE just needs a faster computer. The slowness is fundamental to how it's built. Every input takes seconds to process instead of microseconds, and fewer tests mean fewer bugs found. So even the symbolic execution is theoretically smarter. In practice, it often uses to fuzzing simply because fuzzing can try so many more inputs in the same time. This is the core tension in the paper is trying to resolve. Can we get the intelligence of symbolic execution at something approaching the speed of fuzzing? To understand the solution, we need to understand why CLE is slow. CLE works by converting your program into LLVM's intermediate representation, IR, and then interpreting that IR. It runs through your program's instruction by instruction, and each step that it's doing two things: the normal computation and updating the symbolic tracking data structures. The problem is the word interpreting. An interpreter processes the program's instructions one at a time, dispatching on each opcode, doing work to figure out what each instruction means. And it does all of this work every single time you run the program. Here's an analogy. Imagine you have a recipe written in French and you don't speak French. Every time you cook the dish, you translate each sentence from scratch before following it. Every single time. That translation overhead happens on every execution, even if you have made the dish 100 times. That's CLE. The interpretation overhead, the cost of figuring out what each IR instruction means symbolically, is paid again and again and again for every single input. Before SymCC, the researchers tried to fix this with a system called QSYM, as you see in this figure over here. QSYM takes a different approach instead of interpreting IR. It runs the real compiled binary on the CPU and uses a framework called Intel Pin to inject its symbolical tracking code at runtime. This is called IR-less execution. This is faster, roughly 10 times faster than CLE, because you are running at native machine code instead of interpreting IR. But QSYM has serious problems. To instrument machine code at runtime, you have to handle every CPU instructions, hundreds of them, including all the weird edge cases. That makes the implementation extremely complex. And because it hooks into x86 specific machine code, it only works on x86 processors. No ARM, no RISC-V, no portability. So QSYM is faster but not simple and not portable. And the paper argues it still isn't fast enough. Is there a better way? Yes. And it's elegant. Compile, don't interpret. That's the entire core idea of this paper. If interpretation is slow, because it does work on every execution, the answer is to move that work to compile time. Pay the cost once and then benefit from it across every execution. Think back to that simple recipe analogy. Instead of translating French every time you cook, you translate it once, write the English version down, and then cook from the English recipe forever. The translation cost is real, but you pay it exactly once. That's what SymCC does. Here's how SymCC pipeline works. It's a custom LLVM compiler pass. When you compile your program with SymCC, it interprets the compilation process itself, as you see over here. It sits between the LLVM frontend, which converts your source code into IR, and the LLVM backend, which turns IR into machine code. SymCC's pass walks through every instruction in the IR, and for each one, it inserts code that will perform the symbolic tracking at runtime. The result is a binary that already has all the symbolic handling baked in. When you run it, there is no external interpreter, no runtime hooking framework. The symbolic tracking is just part of the program, running at native speed. And crucially, you only instrument once. Then you can run that binary on as many inputs as you want. This is what SymCC actually does to your code. On the left is a simple function in LLVM IR. It takes two integers and checks whether the first is exactly the double of the second, a totally ordinary function. On the right is what SymCC produces. The concrete computation at the bottom is unchanged. But the program still runs normally, but above it, SymC has inserted a parallel symbolic computation. For every operation, the shift, the comparison, there's a corresponding call to the symbolic backend that tracks what that operation means in terms of symbolic expressions. Both computations run side by side in the same binary. Concrete execution happens at full CPU speed. Symbolic tracking happens alongside it. No external interpreter, no runtime hooking, just compiled code doing two things at once. Now you might worry, isn't all the symbolic tracking code going to slow things down even when you don't need it? Like, if a computation has nothing to do with symbolic inputs, why are we calling the symbolic backend at all? Great question. SymCC handles this with concreteness checks, as you see over here. Think of it like a bouncer at a club. Before each symbolic computation, SymCC inserts a quick check. Are any of the inputs symbolic? If all inputs are concrete, just regular numbers, skip the symbolic backend entirely. Don't bother the solver. In practice, this is a simple null pointer check because SymCC represents concrete values as null pointers. It's extremely fast. Here's how much this matters. Without concreteness checks, 27 seconds. With them enabled, only 0.14 seconds. That's 193 times speed up for code that wasn't even touching symbolic data. Most programs spend most of their time on concrete computation. Concreteness checks means SimCC doesn't pay any price for that. SimCC is built as an LLVM compiler pass, which has some nice practical properties. The implementation is small. The compiler pass is about 1,000 lines of C++. The runtime support library is another 1,000 lines. For a tool that dramatically outperforms years of prior work, that's a remarkably simple code base. Simpler code means fewer bugs in the tool itself, and it means other researchers can actually understand and extend it. Because it operates on LLVM-IR, which is architecture independent, SymCC is portable by design. You can generate binaries for any architecture LLVM supports without changing a single line of SymCC's code. And because many languages compile through LLVM, C, C++, Rust, Swift, Go, adding support for a new language is mostly a matter of making sure the runtime library gets compiled symbolically. One more implementation detail worth understanding how SymCC tracks symbolic expressions as the program runs. Look at this diagram over here. SymCC uses what's called shadow memory. Every piece of data in the program has a corresponding shadow value. If the data is concrete, a regular number, the shadow is null. If it's symbolic, the derived from the user input, the shadow is the symbolic expression. Functional local variables are especially efficient. Their shadow expressions are stored in local variables too, which means the compiler registers the compiler's register allocator can keep them in CPU registers for fast access. The net result is two computations happening in lockstep. The concrete execution in the program is always done, and the symbolic tracking that SymCC baked in at compile time. No external process, no interpreter. So let's just look at how the three systems compare head to head. Look at the CLI column. CLI is simple and portable, works on any architecture LLVM supports, but it's very slow. Now let's look at the QSYM column. QSYM is faster, mm, roughly 10 times faster than CLI, but it's extremely complex to implement and it's locked to x86. Now let's look at the SymCC column. SymCC is near native speed, simple, just 2,000 lines of code and portable across any LLVM supported architecture. This is the key claim of the paper. SymCC is the first approach to be simultaneously fast, simple, and portable. Prior systems made you pick two out of three. Now for the evidence. The authors benchmarked on the DARPA Cyber Grand Challenge program suite, 116 programs originally written for an automated vulnerability finding competition. For pure execution speed, running the programs without any symbolic inputs, SymCC runs at almost native speed. As you can see, native is 1, SymCC is 1, QSYM is 28, CLI is 30. QSYM is 20 times slower, CLI is 30 times slower, and CLI can only even execute 56 of the 116 programs. The rest use features it can't handle. With symbolic inputs enabled actual console execution, SymCC is 10 times faster than QSYM and 12 times faster than CLI on average. And critically, the code coverage they achieve is comparable. SymCC isn't just fast, it's finding the same paths. Faster analysis doesn't come at the cost of thoroughness. Benchmarks on synthetic programs are one thing, real world results are another. And this is where the paper gets genuinely exciting. Open Open JPEG is an open source image processing library. It's the kind of software that processes untrusted files, PDFs, images, which makes it a high value target for security researchers. Google's Oasis Fuzz project continuously fuzzes open JPEG with state of the art tools and significant computing resources. It has been running for years. Zero new vulnerabilities found. The authors ran SymCC on OpenJPEG, one machine, 24 hours. They found two vulnerabilities that OSS Fuzz had not found. Both were heap buffer overflows, the kind of bug that's often directly exploitable. The OpenJPEG maintainers confirmed and patched both. NIST assigned them severity scores of 7.4 and 7.5 and 8.8 out of 10. USYM, running in the same experimental setup, found neither. The graph shows code coverage over 24 hours for three real-world programs. The top line in each panel is SymCC. The dashed line is QSYM. SymCC consistently achieves higher coverage and the gap grows over time. These differences are statistically significant, p less than 0.0002 across all three programs. Why does p translate directly to coverage? Because of the feedback loop. SymCC generates more test cases per second, which feeds back to the fuzzer, which finds more interesting inputs to analyze, which leads to even more coverage. Faster analysis compounds through the loop. It's not a linear relationship, it's multiplicative. This paper makes this joint explicitly. The coverage improvement correlates directly with the speed improvement. This isn't a coincidence. Symbolic execution's value has always been in the quality of its reasoning. SymCC just finally makes it fast enough to matter. This paper is honest about what SymCC doesn't solve, and I think it's worth spending a moment on this. First, SymCC requires source code, binary-only targets, closed source libraries, proprietary software, or are treated as black boxes. This is a real limitation. Second, estimated binaries are about 3.4 times larger, and compilation takes about 58% longer. The compilation overhead is one time, but the binary size increase is always there. Solver, just look at the times. Third, and this is the most interesting, look at the time split. For open JPEG, um, for open JPEG over here, for open JPEG, the execution time per analysis is 1.9 seconds on average with SymCC. But this SMD solver time is 26 seconds. SymCC has effectively solved the execution bottleneck. The new bottleneck is the constraint solver. In a sense, SymCC's success creates a new research problem. Now we need faster SMD solvers for symbol execution. So what do I want you to take away from this? First is the fundamental principle over here, compile time versus runtime. Moving work earlier in the pipeline has benefits in many contexts. SymCC is a clean application of that principle to a new domain. Second, old ideas can become transformative with new infrastructure. The basic approach of compiling symbolic handling into programs was tried in the early 2000s, but LLVM gave the authors the infrastructure to do it properly, language independent, architecture independent, and clean. Third, speed compounds. Faster analysis through the fuzzing feedback loop turns into significantly more bugs found. The two CVs in OpenJPEG prove this isn't just academic. If you want to go deeper, I'd point you specifically to section 4 on the implementation and table 1. The real story is in those numbers. read the paper. That's all I will say. Thank you.